In this video, we're finally going to address the question I had at the bottom last time when I had this reaction drawn, and the question really is, does this reaction go? And like I mentioned in that previous video, fundamentally, we're not interested in acid-base reactions in organic chemistry very much for them. What we're interested in is, does this reaction go enough to allow some downstream reaction to take place? And so ultimately what we care about is sort of order of magnitude type stuff, and we don't exactly care about the details of the numbers. And so what I'm going to walk through here is a more detailed derivation of how you arrive at the key number, and then I'm going to give you a shortcut for this is how you get to the key number. Does this reaction go or not, and how far? And so ultimately, again, what we're interested in is this reaction, and I've drawn out the mechanism for it before, so I won't belabor the point, just simply to show the arrows one more time, and that is the actual mechanism for this reaction. But the question is, does this reaction go to the right, or does it stay over here on the left? Do you make these charged products, or do you stay in this uncharged realm? And this is not necessarily a straightforward question to answer, because if I simply asked, hey, which Lewis structures do you prefer? Absolutely everybody would say these, as opposed to these. You'd rather have the neutral ones than the charged ones, but it may be the case that when you mix these two together, nevertheless, they proceed to the charged state. So let's find out. I've gone through these reactions in some detail before in the previous video, and I've also diagrammed out the mechanisms for it, but in this case, I'm not so much interested in the mechanisms anymore, although of course they are going to go as I'm illustrating now, and that will lead to these products. And the analysis that I just talked about with the making of the charged things, that would argue that this reaction shouldn't go, and in fact, that's the way it is. If you were to look this up, the Ka in a Gen Chem text for this is 1.8 times 10 to the minus 5, which is to say this reaction does not proceed to any appreciable extent. In fact, it stays largely on the reactant side. If you instead take ammonium and throw it in, you might expect, hey, this thing is charged and it should go ahead and generate the neutral, but of course what you're doing is taking this charged thing and transferring the charge to the water. So the question really comes down to which is preferred, the plus charge on the oxygen or the plus charge on the nitrogen. And if you think about that briefly, what you'll realize is, of course, a nitrogen is a less electronegative atom, so it can probably better tolerate the plus than the oxygen. So after you learn that, then it won't surprise you to learn that the Ka for this reaction is 5.6 times 10 to the minus 10, which is to say, if this reaction doesn't go, this reaction is 100,000 times less likely to go than this one is. So this really doesn't go very far. This really doesn't go very far. It stays entirely on this side. Now, I've mentioned before that these are tiny numbers, and you can start to realize just how hard that is to write out all the time. And so instead, what organic chemists have a tendency to do is to say, well, let's think in terms of smaller numbers, easier numbers to remember. And so pKa is on the order of 5 for this. It's actually specifically 4.76 for this one, but to an organic chemist, I don't care about the details, that's 5. And similarly, rather than look at this number with this exponent and so on, what we do is we take the negative log, and pKa for ammonium is specifically 9.25. But again, I'm an organic chemist. I'm kind of sloppy with numbers, and I don't really care, so the answer for me, mentally, that I store away is it's about 10. Obviously, you can see how that rounds. Obviously, this doesn't round, and yet these are useful for the order of magnitude, because what I'm really telling you is this is 100,000 times more likely to happen than this is, and that is captured with the 5 and 10. There's 5 orders of magnitude, 100,000. We're not running these two reactions. We are instead running this reaction. So why did I bother to bring this up? Well, because what I actually have here is a reaction in the middle that's in here, as well as this reaction up here. Now, the problem is that this reaction in the middle is kind of this reaction in disguise, because of course the ammonium is on the product side. Okay, so what that really means is I need to flip this reaction, and that means that the ammonia part needs to be over here on the left, and so ammonia plus H3O plus needs to be over here on the left. And now I'm going to have this equilibrium right over here, and that means that the ammonium is now going to be on this side, and I'm just going to write that as NH4 plus and water. And now, of course, you realize why I took the time in that one video to go ahead and set up what happens when you reverse the reaction. When you flip the reaction, what does that do? Well, it takes the reciprocal for the pKa, or the Ka. Whatever the equilibrium expression here is going to be flipped. And so now, again, the right answer would be 1 over 9.25, but instead, the way I like to think of this is that the pKa is now going going to be minus 10, if you will, for this reaction. Or, said another way, rather than thinking of this as being 10 to the minus 10th, this overall thing is on the order of 10 to the 10th. But again, the pKa for this particular reaction, the pK for this reaction is minus 10, which again is 10 to the 10th. Let's just review for a second what I did. If this reaction doesn't go at all, then this reaction has to be almost entirely on the product side, which is a big number, 10 to the 10th. That's a large number. And since the P function is negative log, the negative log of 10 to the 10th is minus 10. Okay, so the reason why I did this now is because I can now add some reactions together. But now I'm getting confused because I have all this stuff here, so I'm going to simplify things and erase some. Okay, so how do we combine the top two reactions in such a way that we end up with this bottom reaction? So I hope you see that the ammonium is the same on both sides here, and the acetic acid is the same on both sides here. The acetate is on both sides here, but now you'll notice that there are certain things in this expression that are not showing up in this bottom reaction. And so the H3O plus is on this side and on this side. So what we're going to do is we're going to cancel the H3O plus in both cases. We're going to take the water and we're going to drop it out of the expressions too. And what you're left with now when you just simply sum them up is this right here. So now the question, the key question for you is, what do we do with the equilibrium constants when we add reactions together? And the answer is you multiply them times each other. So the K for the overall expression that we are interested in is basically the two K's times each other. Or if you're thinking in log terms, what that is going to be is the two expressions added together. Now, as for why that might be the case, you can go through the derivation yourself. Just remember that what's going on here is the actual K for the reaction that we are interested in is given by the following. K numerically is going to be given by the concentrations of the two products, which is to say acetate minus and ammonium plus, divided by acetic acid and ammonia. But if you work through the equilibrium expressions for these two and then figure out how you get those to add up to that, what you're going to find is you multiply the two together. And in pK land, what you're doing is you're adding, because this is a log expression. Intuitively, what I want you to realize is this. This reaction is extremely unlikely to happen, to the tune of 100,000 in the wrong direction. However, this reaction is extremely likely to happen to the tune of 10 billion in the right direction. So, what happens when you add these two together? What happens when you multiply the two reactions times each other? This reaction is very likely to happen to the tune of 5 pK units, which is to say 10 to the 5th or so. Again, it's 10 to the 10 in this direction, it's 10 to the 5 in this direction, or 10 to the minus 5 in this direction. And what that means is your 10 to the 5th likely to happen as drawn. So even though it's weird because this is neutral as drawn and these are charged, because this is a more powerful reaction, it's driving the process. You end up 10 to the 5th on this side. Now, how do I want you to think about this? Well, what I want you to be able to do is to recognize that between acetic acid and acetate, there is a relationship that I want you to simply memorize and remember, and that is that the pKa for acetic acid becoming acetate is on the order of 5. Between ammonium and ammonia, there is likewise a pKa type relationship, and though I've drawn it out this way as 10 to the minus 10th, what you really want to keep in mind is that for ammonium going to ammonia, the pKa expression there is 10. And again, these are going to be numbers that I just want you to simply memorize on a short list. Carboxylic acid in general is pKa of 5 going to its conjugate base. Ammonium going to ammonia is 10, and that also will be on the short list. A nitrogen with a plus on it in general going to nitrogen neutral is going to be a pKa of about 10. So what you see is on the reactant side we have 5, on the product side we have 10, and therefore what you do is just simply take 10 minus 5, and you recognize that therefore equilibrium for this process is going to be on the order of 10 to the 5th, or probably a better way of saying it is that pK equilibrium for this process is about 5. Again, you take the number over here and you subtract off the number over there, and that lets you say, oh yes, this reaction goes. It goes to the tune of pK units of about 5, which is to say 100,000. Therefore, the number is fairly large, and most of your reaction will be over on this side, and relatively little of it will be on this side.